Okay, so happy to see you all back at the BLT seminar in February, and we'd like to welcome Joe Bonin from George Washington University. Take it away, Joe.
All right, thank you for the invitation. I appreciate this, and thank you for being accommodating about the day. And I know this usually meets Wednesdays, but problem on Wednesdays. um, so I'm going to be talking about identifying some vertices of the polytope of matroids. Let me start by mentioning the plan of the talk. So the polytope of matroids has relatively recently been introduced by Alex Fink and Luis Ferroni. So it may not be familiar to everyone. So I'm actually going to spend the first roughly half of the talk just on general background on the polytope of matroids, because that's what motivates these results. Um, as usual, I have my slides posted on my webpage, so you can get them there. The paper is there, and until February 21, a free copy of the published paper is also there. I'm going to assume that people at least know basics of matroid theory, what a matroid is, bases, and so on. But I will start with some particular matroid background that we're going to use. And so the first of that background is on cyclic flats. So in general, a set in a matroid is cyclic if it's a union of circuits. And that's equivalent to saying if you restrict it to that set, you don't have any co-loops. Now, what we're interested in most of all are the flats that are cyclic. So those are called cyclic flats. And we let ZM denote the set of these cyclic flats. So here are two examples that I'm going to use as running examples in the first part of this talk. So in the upper one, we have as our cyclic flats the empty set, the parallel points AA prime, BB prime. There's the line that they form. So that's this A union B here. And then the line with the A's and the C's, the lines with the B's and the D's, and the whole thing. And this is a very similar example. Um, we have the A and the B, but now A is in three cyclic lines, A union B, A union C, and A union D, whereas B is in just one, the A union B. Okay. Now, you might actually recognize this. If I simplified this and got rid of the parallel points, just reduced them to a single point, then I would have the standard example of the smallest pair of matroids with the same Tut polynomial. Okay. It's a variation on that, but interesting things happen with this variation. All right. Um, it's a basic fact that matroid is determined by its cyclic flats and their rank. You could actually write down the rank function of the whole matroid in terms of the cyclic flats and their rank very nicely. Um, the cyclic flats always form a lattice. You know, all flats form a lattice. They form a geometric lattice. Out of the cyclic flats, you can actually get any lattice up to isomorphism, any finite lattice. How do you see that it's a lattice? Well, if you have two cyclic flats, their closure, the union of the closure, well, that's going to be automatically cyclic and it's a flat. So that's fine. And if you take the intersection of two cyclic flats, you get a flat, but it might have some co-loops. Oh, just get rid of the co-loops. That gets you the meat. So you really do have a lattice here. Now, some classes of matroids that are going to be quite important are nicely defined in terms of their cyclic flats. In particular, we're looking at nested matroids. So nested matroids are matroids where the cyclic flats form a chain. You take any two cyclic flats, one is contained in the other. Okay. We're also going to be interested in isomorphism types of matroids or matroids up to labeling. And we're going to illustrate that with nested matroids because that, looking at unlabeled nested matroids is going to be very, very useful. A way to get a nice representative for a nested matroid is to take a lattice path, say going from 0, 0 to n minus r, r. N is going to be the number of points, r is going to be the rank. So all of these paths consist of n steps, r of them are north. And then you look at paths that stay on or below that path, such as, so our bounding path is the red path, Q, and then a path that doesn't go above that would be Q, for instance. And with such a path Q, you can simply look at where the north steps occur. So in this case, it'd be 3, 5, 6, and 8. That gives you a set. If you look at all of the paths from 0, 0 to n minus r staying in that region, with each associate this set, that collection of sets is the set of bases of a nested matroid. Okay? The cyclic flats wind up being the initial intervals up to a east-north corner. Okay? So, well, there's sort of the trivial one, the empty set, and then 1, 2 would be a cyclic flat, 1 through 5 would be a cyclic flat, and the whole thing would be a cyclic flat. So they form a chain, and it's an initial segment of the integers 1 through n. I mean, you can get a sense of that by, 1 and 2 are obviously parallel because you can't put them together in any path. And then among the first 5, you can have at most 2 elements, but you could add anything else after that. So you have a flat and it is cyclic. So that tells you, well, the number of these nested matroids of rank R on n elements is just the number of paths from 0, 0 to n minus r. So that's n choose r. Okay? So that's a nice way to represent nested matroids. Now, there's a polytope of matroids behind this whole thing. Before we get to that, we need to talk about matroid-based polytopes. So when you take a matroid, you can represent its bases as the vertices of a polytope. So when you do this, you're thinking of the matroid on the ground set 1 through n. With each basis, you can take its characteristic vector. It's just the 0, 1 vector telling you which elements are in the basis. And the matroid-based polytope is the convex hull of those. So to give a concrete example, if you look at U24, and this is sort of the standard example people draw because it's one of the few you can actually draw. If you look at U24, so you have 4 points in general position on a line. Any 2 give you a basis. So your bases would be the 2 element subsets of 1 through 4. You look at the corresponding 6 points in R4, and those give you the vertices of the base polytope. And the edges of that polytope tell you about basis exchange and things like that. So that's the matroid-based polytope. All right. Now we're going to do sort of a similar thing to characteristic vectors, but at the level of polytopes. So the indicator function of a matroid is the function on Rn. So you have a matroid on n. So you're talking about, n tuples in the matroid-based polytope. Excuse me. The indicator function is just this function on Rn that tells you whether or not a point is in the matroid-based polytope. So it's 1 if the point x is in the polytope, if 0 otherwise. So it's like a characteristic vector, but obviously adapted to being on Rn. And with that, we can now give this interesting result due to Dirksen and Fink in 2010. If you take a rank R matroid on n elements, and you look at all of the nested matroids of rank R on the same set, then the indicator function of the matroid can be written uniquely as an integer linear combination of the indicator functions of the nested matroids. That raises 2 questions. Which of these coefficients are non-zero? And how can you actually find those integer coefficients? And Hampe answered this in 2017. So what he has is, if AI is not 0, then this chain of cyclic flats in Ni is actually a chain of cyclic flats in your matroid. It has to include the least and greatest cyclic flats in your matroid, and the ranks are the same. So you're talking about a real chain in your matroid going from from the bottom to the top. And there's an explicit formula for the coefficients. So what you do to get the coefficients is you have to look at the lattice of chains. So you take all of these chains of cyclic flats in your matroid that include the smallest cyclic flat and the greatest cyclic flat, order them by inclusion. Now, of course, you have intersections of chains as a chain. That's great. Unions of chains, that's a problem. Okay, so you add an artificial top. Okay, so there's the one hat. And then you have this lattice of these chains. The coefficient of Ni, or the coefficient of chain, is going to be minus the Moebius value from that chain to the top. Now, let me give you some examples to make this nice and concrete. We're going to use those two standard examples that we have. So in these examples, slide is pretty cluttered. To make it a little less cluttered than it would otherwise be, I'm suppressing the least and the greatest cyclic flat in these chains. So for instance, when I have A here, that really means empty set A, EM. Similarly for the others. So I would have, the empty set A, AC, EM is no larger. So that's at the top, right under the one hat. All of these, of course, get Moebius value -1 because the sum of the Moebius value over an interval has to be 0. A, that's covered by two of these chains. I could add AC to it or AB. So I have, both of those getting -1. I have a 1 up here. Oh, this has to be Moebius value 1 to balance it out. On the other hand, if I look at A union C, there's only one way to extend that, namely put in A. I already have 1 and -1 summing to 0, so this gets 0. So I can just compute all the Moebius values this way. Similarly, down here, we get a lot of -1s at the top, all -1s at the top. But these examples differ in that, notice the A and the B here get both a 1, whereas here B gets 0, but A gets 2, sort of balancing things out still. Okay? So that's an example of actually computing these coefficients. Now, valuative invariants. So what are valuative invariants? Well, they're matroid invariants, so they depend just on the isomorphism type of the matroid. And they have this nice property that when you look at how the indicator function of M is expressed in terms of the indicator functions of nested matroids, the invariant satisfies exactly the same relation. And so that's what valuative invariants are. That's one of several ways of describing what valuative invariants are. There's also ways in terms of polymatroid decompositions and whatnot. This is the one that, well, is the quickest to get to for this. And yeah, it fits what we're going to do. So that's what valuative invariants are. I'll give you a lot of them shortly. Now, because valuative invariants just depend on the isomorphism type of the matroid, there's going to be a lot of collapsing when you evaluate this. A lot of these nested matroids are going to be isomorphic, so they're going to give you the same value. So we'll have to take that into account. So so in this case, this one of our running examples, those nested, those chains at the top, oh, they're this type of nested matroid where you have, a parallel pair and then two more points on a line and then the whole thing. So I have 4 of those -1s. That translates into 4 times whatever the invariant is on this nested matroid. And then these A and B, they give you this nested matroid, right? You have the parallel pair, but not the line. I have 2 contributing a 1. Oh, so that's going to be my -2 F on this nested matroid. And then this guy, that's just the cyclic line and the whole thing. So that's going to be -1 copy of whatever F produces on this. Okay. Let's see, do things change for the other in our pair of examples? They don't, right? Instead of having these 2 1s, I have this 2. So I get the same coefficient here, and the rest of it lined up anyway. So yeah, these two non-isomorphic matroids are going to have the same valuative invariance. Now, valuative invariants depend, they have the same value on isomorphic matroids. So it'd be nice to have a variation of the indicator function that depends just on the isomorphism type rather than the actual matroid. And this is achieved by the symmetrized indicator function. So what you do to get the symmetrized indicator function is you sum over all permutations of the ground set, so basically all possible relabelings. You take your indicator function, you evaluate it at the permuted variables, and you take the average of all of those. Okay? So that's the symmetrized indicator function. And you still get the same result. If you take, a matroid on n elements, rank R, and you look at the unlabeled rank R nested matroids on that ground set, then there are unique integers so that the symmetrized indicator function of M is that combination of the symmetrized indicator functions of the nested matroids, the unlabeled nested matroids. Okay. Yeah. I think there was something I wanted to add at this point, but it's not coming to me right now. So yeah, there are fewer matroids, fewer unlabeled matroids, of course. But yeah, you still get the same collection of coefficients. All right, so that leads to this polytope of unlabeled matroids, because with each matroid, you then get this n plus r tuple of integer coefficients. And you can just take, that point for every matroid, take the collection of them, take their convex hull. That is the polytope of unlabeled matroids. Of course, when you're interested in a polytope, it's nice to identify the vertices because that tells you a lot. The vertices of the matroids that give the vertices are called extremal matroids. And Louis Ferroni and Alex Fink have a very nice characterization of them. So what this theorem says is, if you start off with a set that contains one copy of each isomorphism type of rank R matroid on n elements, and you pick a sequence of real valued valuative invariants, you take your initial set, and then you look at the matroids that maximize the first of your valuative invariants. And then that gives you a smaller set. Within that, you look at the matroids that maximize your second, and so on. So you're maximizing a sequence of valuative invariants. If in the end, the final trimmed down set either consists of a single matroid or a collection of matroids that all give the same point in the polytope, then that point is a vertex. So those matroids are extremal. So that's the sort of thing that I'm going to be doing in this talk. I'm going to be finding for certain matroids sequences of valuative invariants that hone in on that matroid or that collection of matroids. Okay. By the way, feel free to ask questions and stop me at any point. I want to make sure things are clear to everyone. So, all right. Hearing no complaints, move on. So to give some examples of this, so this is an example that Alex and Luis had in their paper. The number of bases, of course, is a valuative invariant. So what maximizes the number of bases? Well, uniform matroids. So uniform matroids are extremal. Here's another example, a pair of examples that's going to motivate some of the results in this talk. So one of the many valuative invariants, and I'll give you a sense of what valuative invariants are shortly, concretely. One valuative invariant is the number of flats of a given rank, say rank K, and a given size, say size S. Okay? So if you're looking at rank 3 matroids on 7 elements, the first thing you can do is you can look at maximizing the number of rank 1, size 1 flats. Well, that eliminates loops and that eliminates parallel elements, so that gets you down to simple matroids. Okay? And then within simple matroids on rank 3, 7 elements, you can maximize the number of 3-point lines. So F sub 2 and 3. Well, that maximum is 7. The only way to achieve 7 is the familiar projective plane on 7 elements, the Fano plane. Oh, so the Fano plane is extremal. Similarly, you can do that with the cycle matroid of K4. Now, first, maximize the number of rank 1, size 1 flats to get down to simple matroids. Maximize the number of 3-point lines. The maximum is 3. The only way to achieve the maximum is this configuration. That's extremal. Okay. We'll generalize this first one to arbitrary perfect matroid designs, which include projective geometries, affine geometries, and a whole bunch of other stuff. We'll extend this one to all complete graphs, cycle matroids and complete graphs, their truncations, and more. Okay, it's good to see some examples that aren't extremal, just to get a sense of what this really involves. Not all matroids are extremal. So let's go back to our example. So we have the indicator function of M is 4 times, so for that initial matroid, is 4 times the indicator function of this nested matroid minus 2 copies of the indicator function for this minus 1 copy of this. So if you scoop the terms with negatives over to the other side and divide by 4, what you see is this nested matroid is an affine combination of these other 3 indicator functions. That tells you this guy is not a vertex. It's not a vertex of the polytope. So, I mean, at first I found this a little disturbing. Actually, Alex and Luis gave a smaller example of a nested matroid that is not extremal. But yeah, at first you might suspect all the nested matroids that play such a role here, they should be extreme. No, that's not the case. It's an interesting question which ones are. It's not at all clear. Okay, so what are these valuative invariants? I mean, we've given a definition, but concretely, what sort of things are they? Well, fortunately, like the Tut polynomial being a universal deletion contraction invariant, there is a universal valuative invariant. It's the G invariant. By the way, the Tut polynomial is valuative, but valuative goes way, way beyond Tut polynomials. Okay? I should also say this is also a place where sort of the structural world and the enumerative world differ a lot. The important structural invariants like connectivity, vertical connectivity, branch width, those are not valuative. So what's this G invariant? Well, let's start with rank sequences. So start with a matroid, take a permutation on the ground set. Think about adding the elements in your matroid one at a time in the order given by the permutation. So we'd start with the empty set, then we'd add 5, then we'd add 2 to that, we'd add 6 to that, 4 to that one. Each time the rank either stays the same or goes up. You just record those rank increases. If the ranks increase, we put a 1. If the rank stays the same, we put a 0. Okay? So with each permutation, we get this 0, 1 sequence indicating whether or not the ranks went up. What you can then do is basically take a generating function for all these kind of rank sequences. So formally, with each possible rank sequence, each of these 0, 1 sequences, we could consider a variable. And then we can consider the vector space where those variables give you a basis. And the G invariant is just the sum over all permutations of the rank sequence, the variable. So for instance, if we do this with the cycle matroid of K4, well, your first 3 elements in a permutation either are a basis, so giving us 1, 1, 1, 0, 0, 0, or you would have 3 points on a line, and the next would complete a basis with the first 2, for instance. That would give us a 1, 1, 0, 1, 0, 0. How many do you have of the first type? Oh, well, how many bases do you have? That's Cayley's theorem, n to the n minus 2. So there's 4 squared. And then put the basis elements in order, put the rest in order, 3 factorial, 3 factorial. For these guys, Well, you could start with any point, any of the 6 points. Any point is on two 3-point lines. So there are 4 points that I could choose next. That's the 4. The next choice to complete a line that would be determined. And then you have to put the other 3 elements in order. So you get this strange looking object as the G invariant. But you can dig a lot of information out of this. Yeah, the G invariant is a universal valuative invariant. To get all other valuative invariants, what you'd simply do is, you want to get valuative invariants into a particular abelian group, just assign for each of these variables associated with rank sequences some image and extend linearly. Among the interesting valuations or instances of that, well, map a particular rank sequence to 1, all the others to 0. That picks off a particular coefficient. Another interesting one is take your rank sequence, switch zeros and ones, and write everything backwards. Oh, that's the rank sequence you'd get out of the dual. So yeah, the G invariant of the dual is a valuative invariant of the original matroid. So here's a list of the relevant for us valuative invariants. For other, I mean, there are lots of other ones that come up in other contexts. The G invariant and its dual, that coefficient of a particular rank sequence in the G invariant, the Tut polynomial, any particular coefficient of the Tut polynomial, we'll use those. Information you can dig out of the Tut polynomial, such as the number of independent sets, the number of bases, and then this catenary data stuff that Joseph Kung and I worked on. If you pick 2 particular ranks, H and K, and for each rank in between those, pick a size, and then you look at all of the flags of flats of those ranks with those specified sizes, the number of those flags is a valuative invariant. A particular case of that is the number of flats of a given rank and size. We've already seen that used, right? Also, the number of flats of a given rank, given size, where the restriction has a given number of coloops. That's a useful valuative invariant. So those are some of the valuative invariants out there. Well, in some sense, the G invariant is all of them. It encompasses all of them. But for particular ones, those are some of the ones out there, the ones that we're going to actually use. Okay. Another useful result in the last of the background is this, that if 2 matroids have the same G invariant, they actually determine the same point in the polytope of matroids. The polytope of matroids really is sort of set up to correspond to the G invariants of matroids. So yeah, as a result, if M and N have the same G invariant, one is extremal if and only if the other is extremal. So just to make that concrete, if we look at all projective planes of a given order, it's easy to check that they all have the same G invariant. So once we show that they can be characterized by a sequence of optimizing valuative invariants, then it follows, yeah, they all determine the same point. That point is a vertex. It's extreme. They're all extremal. Okay. So that concludes the background. Any questions before I get to the results? All
Sorry,
right.
I have one question.
Sure.
Is every integer point in the polytope a matroid, or is every point in the polytope a matroid?
Integer point. So that's a question. I noticed Alex was here. He might be able to answer that. I don't know the answer to that question.
The
Okay.
answer is no. Near the end of my paper with Lewis, there's some examples. Lewis computed some in 3.6, I think.
Okay. Okay, great. But at least every vertex is a
That's right.
matroid. Okay. Okay, thanks.
Thanks, Alex. So the first of the results, So Luis and Alex conjectured that projective geometries are extremal. Now, projective geometries kind of stand out because all of the flats of a given rank have the same size, right? All subspaces of the same dimension have the same size. Just generalize that. So perfect matroid designs are matroids where you have a sequence of integers, alpha naught, alpha 1 through alpha rank of m, so that all flats of size of rank I have size alpha I. So projective geometries, affine geometries are also examples. Their truncations are examples. But there are a lot of other examples. So for instance, um, you can find paving matroids where all of the hyperplanes have the same size. Those are actually Steiner systems. So Steiner systems give you other examples. Perfect matroid designs are extremal. What you do, in fact, you just need to maximize one valuative invariant. You take this sequence of the sizes of the flats, you look at matroids where chains, flags with those sizes are maximized, you have a perfect matroid design. Okay, so this includes, projective geometries, affine geometries, a whole lot more. Okay. And the G invariance is determined by that same sequence of flat sizes. So yeah, these really are vertices. So that's a simple example to start with, generalizing the F7 example that I showed before. So Alex and Louise conjectured that cycle matroids of complete graphs are extremal. So that's one of the results here. And here is the characterization in terms of maximizing a sequence of valuative invariants. So we're assuming that M is a simple matroid of rank R on R plus 1 choose 2 points. So the rank and the number of points, that's fixed for the polytope. So that's fine. We've already seen we can determine simple by maximizing the number of rank 1 size 1 flats. So that's easy. We're assuming that all lines have size 2 or 3, that all planes have size 3, 4, or 6. And for larger ranks, rank H flats have at most H plus 1 choose 2 elements. Of course, H plus 1 choose 2, that's for a smaller complete graph on H plus 1 vertices. Given those conditions, we can show that there are at most R plus 1 choose 3 lines of size 3. And if you have R plus 1 lines of size 3, then you have a cycle matroid of a complete graph. So the important thing here is, how does this actually fit their theorem? Remember, their theorem is about optimizing a sequence of valuative invariants. I should say maximizing is the same as minimizing. F is valuative if and only if minus F is. So, whether we maximize or minimize, it's fine. Maximizing the number of size 1, rank 1 flats, that focuses on simple matroids. Then we have these conditions about all lines have size 2 or 3. Oh, great. Minimize the number of flats, number of lines of other sizes. All right, that gets all of your lines down to those sizes. Similarly, our restrictions on planes just minimize the number of planes of other sizes. Then we show that under those conditions, the number of rank 2 size 3 flats is at most R plus 1 choose 3. Inequality holds precisely. So it's exactly this sequence of maximizing a sequence of valuative invariants. Okay, does everybody see how it fits their theorem? Now, how do we actually prove this? Well, we prove this with a result that is older and is close to this, but not quite there. So 25, 30 years ago, I was very interested in characterizing, or finding matroids that are Tut unique, matroids that are determined up to isomorphism by their Tut polynomial. It turns out there's a very strong connection, not an implication either way, but sort of same ideas, same tools between these extremal vertices, the extremal matroids in this sense, in the polytope sense, and tight unique matroids. So with my first PhD student, Bill Miller, we came up with a numerical characterization of the cycle matroid of complete graphs, which actually was built on an earlier geometric characterization. Cycle matroid, excuse me, if K r plus 1 is the unique rank R simple matroid that has R plus 1 choose 2 points. It has R plus 1 choose 3 size 3 lines, no 5-element planes, R plus 1 choose 4 size 6 planes, no larger planes, and no rank 4 flats exceeding 10. Okay? So this isn't really optimizing things. It's just saying here is the line size. Here is, the sizes of planes and so on. Okay. So this doesn't really show that it's extremal, but it's a useful stepping stone. So it really doesn't, it's not optimizing valuative invariants. But it's useful. So how do we actually prove this result? So let me just give you a sketch. You first show that in any, so if you fix a point and you look at a rank H flat that it's in, you argue that, oh, it's in at most H minus 1 size 3 lines. Okay. And so it's in at most globally R minus 1 size 3 lines. Well, then you can do a little counting with how many point and 3-point line pairs do we have, right? And that gives you an upper bound on the number of 3-point lines. Okay. Then the real work comes in arguing that all the 6-point planes in fact look like MK4, cycle matroid of K4. With that, and again, counting, you get, counting 3-point lines in 6-point planes, you get the number of, in the extremal case, you get the number of these full-point lines. Sorry, you get the number of these MK4 copies, planes that look like MK4. And then so you can verify the properties in the earlier result. So that's how we go about proving this. That's one characterization of the cycle matroid of K r plus 1. It's useful for proving other characterizations, and this characterization is actually useful in turn in proving that direct sums of cycle matroids of complete graphs are also extremal. So that was a further part of this. So this result says, again, we have a simple matroid rank R on R plus 1 choose 2 points. What we're assuming here is that for each I less than R, rank I flats either have I plus 1 choose 2 elements. So you can think of those as, complete graph on I plus 1 vertices, or their size is at most I plus 1 choose 2 plus 1. So you can think of that as bounded by a graph on I vertices together with an edge separate. So call those largest ones the large flats, and call a flag large if each of its flats is large. Then the number of these large hyperplanes, so that's a valuative invariant, is at most R plus 1. And the only time it is R plus 1 is the cycle matroid of the complete graph. Likewise, the number of large flags is at most R plus 1 factorial over 2. And the only time you achieve that is a cycle matroid of the complete graph. So those are, two more ways of realizing that this cycle matroid is extremal. And quick sketch of the proof of this. It's, again, a lot of counting, just showing that the intersection of two large hyperplanes has to be a large flat of rank R minus 2. And all of those intersections are different. That, once you check that, then you can get this bound on the number of large hyperplanes inductively. But then you can also iterate that. Well, what about the intersections of those? Okay. And that winds up telling you how many large lines you have. And so the previous result applies. So that's how that one is proven. But then there's a variation on the theme. The truncations of cycle matroids of complete graphs are also extremal, provided those truncations still have rank at least 5. So that's the one limitation of this result. It works only for ranks at least 5. Now, I should mention this was inspired by a tut uniqueness result that Anna Demier and Mark Noy have for truncations of complete graphs. So this result says, again, you have a rank, you have a k. This is how many times you're going to truncate. You want r minus k to be at least 5. So truncation, I should say, in case it's not familiar, what you're basically doing when you truncate once is you're saying, oh, your bases of your truncation are the bases of hyperplanes of your original matroid. Okay, so bases of one smaller. In terms of flats, you've removed the hyperplanes from the lattice of flats. So you're sort of pushing the whole thing down into a smaller dimension. Yeah, so if we have a simple rank r minus k matroid on r plus 1 choose 2 points, where for proper flats other than the top, their size is at most the rank plus 1 over 2, and there are no size 5 planes, then you get the same bound as before on the number 3-point lines, r plus 1 choose 2. Now, if you're in that extremal case where you have r plus 1 choose 2 lines of size 3, then M has at most as many independent sets as in the truncation of a cyclomatroid of a complete graph. And in that extremal case, if you have the same number of independent sets, then yeah, you have the truncation of the cyclomatroid of a complete graph. So there, it's extremal. Now, how do we actually go about proving this? The first part is just adapting what we did earlier to get the bound on the size of 3 lines. Once you have that, in the extremal case, you can actually identify your collection of 3-point lines with the 3 cycles in the complete graph. With that identification, you get an inclusion of the independent sets of M as independent sets in the cyclomatroid of the complete graph. And so if it's the same number of them, it's the same. So that's how we prove that. So yeah, that's those are results on cyclomatroids of complete graphs. What about projective geometries and things? Well, we've already seen full projective geometry, but here's an interesting projective or variation on projective geometry. These are the Bose-Burton geometries, and I'll get to the characterizations of them soon, but let's just talk about what they are. So everybody knows Turan's theorem in graph theory, where you have, a graph on n vertices, and you want to avoid having complete subgraphs of a given size. A counterpart of that for projective geometries would be you want to look at a restriction of PG_r-1q that has no PG_m-1q restrictions. Okay? It's like not having a complete subgraph. Well, okay, so if you're in dimension R and you want to avoid complete subspaces of dimension M, remove a space of dimension m minus r plus 1 because it would have to intersect any m-dimensional subspace. And what the Bose-Burton theorem is saying is, yeah, that's exactly the extremal case, right? You have an upper bound on the number of points that is the size of PGR minus 1 with the size of PGM minus 1, r minus m removed. And the extremal example is exactly that. And so that's why these Bose-Burton geometries are interesting because of this theorem. They turn out to have a lot of other interesting properties. Well, one thing that they are is tut unique. That's why I was thinking about them years ago. So here's a result with another of my students from years ago. It's a characterization of most of the Bose-Burton geometries, not all of them. And instead of reading all the details, let's just notice, this applies only if I'm looking at PGR-1q delete PGK-1q, where k is less than r-2. So there are 2 exceptions that I'm not dealing with. And then it's just a matter of saying, well, flats of a certain rank have at most a certain number of elements. Flats of these rank have, just these options for elements. So it all fits into that pattern. So this covers most of the results. So the interesting thing is, what doesn't this cover? So this doesn't cover PG R minus 1Q remove PG R minus 2Q. Of course, that's an affine geometry. That comes under the perfect matroid designs. So the interesting thing that it doesn't cover is PGR minus 1Q delete PGR minus 3Q. So for instance, a projective plane with a point removed. Okay. Well, here's a characterization of those in terms of maximizing valuative invariance. So we have a Q that's at least 2. M is a rank 3 simple matroid on Q squared plus Q points. So we've deleted 1 point from a projective plane. Each line has size Q or Q plus 1. What do we want to maximize? We want to maximize, or actually, minimize. We want to minimize the number of Q point lines. Number of Q point lines is at least Q plus 1. The only time it is Q plus 1 is if you're talking about a single element deletion of a projective plane. And so all of these single element deletions of projective planes are extremal. Let me just give you a sketch of that. You first just argue that every point actually needs to be in a Q point line, because otherwise Q would have to divide the number of points outside of a given point. It'd have to divide Q squared plus Q minus 1, which it doesn't. So every point is on a Q point line. And then you'd use this very sophisticated technique called factoring. Q squared plus Q, the number of points is Q times Q plus 1. So what's the minimum number of Q point lines you could have? Oh, Q plus 1. So that's it. So yeah, not exactly high level stuff here. The only time you're going to get Q plus 1, though, is if each point is in exactly one Q point line. So all the Q point lines are disjoint. Oh, well, in that case, you can just put one more point back on them. You have a modular cut and you can do an extension. But yeah, you can just put one point back on them. You get your projective plane. So in the extremal case, you definitely have a 1-point deletion of a projective plane. And then with that, well, you can argue that all of these things have the same G invariant. So they all determine the same point. So they're extremal. Okay. So that's how you deal with single point deletions of projective planes. Now, you can similarly deal with a projective geometry, remove a flat of rank R minus 2. It has the same flavor. It gets a little more involved. So I'm just flashing the result up there, but I don't think that, going through the details is going to, be that exciting. So let's instead turn to a different direction. So Louise and Alex observed that, uniform matroids are extremal, right? Maximizing the number of bases. They have a conjecture, and this is one of their conjectures that really intrigues me that I have not been able to prove, that direct sums of extremal matroids are extremal. What I can prove 2 results about direct sums, and this is one of them. Direct sums of uniform matroids are extremal. Now, it takes a modest amount of work for this result, and a lot more work for the other result that I'll describe a little bit in a moment. Yeah, their conjecture is likely to be very hard. So to prove this, let's see. Let's take a direct sum of uniform matroids. Let's order them so that the ranks don't go down. And if 2 ranks are the same, well, put the one with fewer elements later. You'll see why I want to do this in a moment. Now, standard arguments, you can deal with loops and co-loops. So I can actually assume each of these is a connected matroid of, rank greater than 0, no co-loops, okay? So that means significance is that this now actually has K components. So how do you restrict your attention to matroids with k components, with exactly k components, by looking at valuative invariants. Well, the Tut polynomial tells you about the number of components. Okay, a matroid is connected if and only if the coefficients of either x or y, both, in the Tut polynomial are non-zero. Then you can extend that to k components. So by minimizing all of the coefficients x to the I, y to the j in the Tut polynomial where I plus j is less than k, you can guarantee there are at least k components in your matroid. We want exactly k. Well, okay, minimize the number of cyclic flats because every component in this case is going to wind up being a cyclic flat. So we would have minimizing this when your cyclic flats are just direct sums of components. And that has the nice property that then there are no proper cyclic flats in those components. So you're getting exactly k components and they're all uniform. Now, this ordering that I put on the ranks and then, or the matroid so that we have these inequalities on ranks and then elements, that's saying if you look at the corresponding 0, 1 sequence, that's lexicographically first among the rank sequences that occur in this matroid. It also encodes all of the ranks and sizes of these components. So what you then need to do is minimize the coefficients of rank sequences that are before this, and then maximize this rank sequence, and that picks out the uniform, this direct sum of uniform matrices. Okay? So you have to work a lot harder for this than for uniform matroids being extremal. So, and now to wrap up, let me mention just other results that we have. If people are familiar with Dowling geometries based on groups, they are sort of group theoretic counterparts of complete graphs. They are determined by, up to the group order of group by their Tut polynomials. But you can use the techniques here to show that, in fact, they're extremal. They all have the same G invariant. Joseph Kung and I showed that years ago. But yeah, they actually determine a vertex. So you can pick them out. There's actually a counterpart of this for certain bicircular matroids that I didn't think of in time, but I'm going to have to put it in some future work. But it actually follows the same lines. Binaries, spikes are very important matroids in structural matroid theory. They're matroids you can think of as just, a bunch of 3-point lines meeting at a point sort of as freely as possible up to some restrictions. Binary spikes are extremal. Spikes that you get by taking parallel connections of lines of the same length and truncating to a given rank, those are extremal. I mentioned there's a harder result about direct sums that I'm not even going to try to describe here. But it covers direct sums of very special types of matroids. So with that, we can prove that direct sums of cycle matroids are complete graphs. They're going to be extremal. Direct sums of projective geometries of rank at least 4 in the same order are extremal. I can add planes if there's only one plane of that order. Similarly for affine geometries. And then if there's a unique group of given order, this will apply to the Dowling geometries based on that group also. Now, I can't mix within those categories. So it's a very kind of restrictive result, but sort of the best we know at this point. Open questions. So, of course, this question that Alex and Luis raised about direct sums, I think that's a very, very interesting question. There's the broader question of what matroid operations preserve being extremal, and Alex and Luis noted duality does. So that's one operation. I mentioned parallel connections to Luis, and he's very dubious about that. So I don't know that, I don't have any reason to suspect that parallel connections of extremal matroids are extremal, but maybe some are. Maybe some parallel connections of uniform matroids, maybe a given uniform matroid at a given point. I mentioned that these Bose-Burton geometries, they're counterparts of the theorem is a counterpart of Turan's theorem. Well, actually, I haven't addressed this question for Turan graphs. Right? Are cyclomatroids of Turan graphs extreme? That's a good problem. Similarly, you can ask, well, what about complete graphs, complete multipartite graphs? Are they're cyclomatroids extremal? The tight uniqueness result for those is known. Anna Demir and Mark Noy have a result about that. And then this question of which nested matroids are extremal. That's very, very open. And the last thing I want to leave you with, it's always good to give some homework. So if you're seeing the polytope of matroids for the first time, and you want to get a feel for how these things really work, here's a good example to work out. You have the three whirl, so this is a relaxation of the cyclomatroid of K4. You're relaxing one of the circuit hyperplanes. If you relax another one, you get this matroid Q6. So it's a good little exercise to show that the indicator function of the three whirl is actually the average of these other two indicator functions. So that shows that the three whirl is not extreme. And of course, since I have homework, it's good to have a bonus too. And the bonus is see how far you can run with this example. This example just suggests a lot of things. And yeah, you can relax all kinds of things and get results similar to this. So that is the end of my talk. Thank you for listening and happy to answer whatever questions you have.
Well, thanks, Joe. Questions from the audience? Maybe while they're thinking, I've got to ask, could you clarify what was there a relationship between tut uniqueness and the extremal property?
So there's a very similar flavor, but neither implication holds. So for instance, we've seen that nested matroids don't have to be extremal. Oh, but they are tut unique.
Right.
And going the other way, some tut unique, some extremal matroids. The Dowling lattices, Dowling geometries, they are not tut unique. You can recover, so you can tell that a matroid is a Dowling geometry from this tut polynomial, but you can't tell which one it is. But yeah, they are extremal because in fact they all have the same G invariant. So yeah, the fact that matroids with the same G invariant give you the same point here, that's allowing you to do some things that you can't do with tut uniqueness. So yeah, there's no implication either way, but there's a very common flavor and similar tools.
More questions?
I have a question. First, thanks for the very nice talk. Can you go back one slide, please?
Sure.
So for example, on this second one, you say duality preserves being extremal. Does that correspond to some uh, to some automorphism of the polytope somehow? Like maybe it's centrally symmetric or something? Or can you say anything about the structure of the matroid polytope?
So I don't have a ready answer for that, but I remember in